So, we continue our discussion with the mooring cable. So, last class we I have derived all these equations. Now, seabed conditions that we have said, seabed conditions. So, we have x 0, there is a horizontal distance, we are starting with x 0 equal to 0 and z 0 is the depth at seabed. So, this is equals to minus h. What are the other conditions is h 0, that is the length of the chain cable at the origin. So, this is your our origin point is here. So, this is your origin point. So, obviously, s you bring it to 0, it will be 0. Now, s 0 we are starting this is equal to 0 and there is another option, that is the angle, that is phi, the angle of inclination of the tangent of the catenary with the x axis, that is this is equal to 0 at the origin. So, this you can state these are at seabed at origin. At seabed at origin point. I think this, I think you could make it clear actually. So, from this we have derived the equations, that is our length, we have put the boundary conditions and we have got that s minus s naught is equals to how much? This is t prime 0 over w cos phi naught tan phi minus tan phi naught. Now, if your phi naught is equal to 0, then this obviously will be equal to 0, cos phi naught will be equal to 1. So, s naught is, we are saying that s naught equal to 0. So, our expression simply becomes at seabed. So, this will be, and what about T naught? So, T naught we have derived in your earlier expression, that T naught is equals to T h at seabed. So, this T h is equal to T prime naught. So, here we get, so our equation becomes T h over W multiplied by tan phi. So, this equation you can write this, I do not know your serial number, you check. So, in my 15. So, this is equation, this should be equation number 15. So, this one equation we have got from the length of the chain cable. Now, from the horizontal distance, you simplify, you put the boundary conditions. So, x minus x naught is equals to so this we have I have derived actually last class. Now, since most of you are coming late, so just repeating actually, but we will start with this. So, this is sec phi naught. So, plus tan phi naught. So, this we have simplified into x naught is equal to 0. So, this comes down to T h over W log of 1 by cos phi plus tan phi. So, this you can write this as 16, or and the other equation, that is the vertical projection, we have derived this as z minus z naught, but z naught is not equal to 0. So, this you be careful when you are substituting, z naught equal to minus h. So, this is t prime naught over w cos phi naught into 1 by cos phi minus 1 over cos phi naught. Here there is not much of the mathematics. So, this becomes z naught is minus h. So, this becomes z plus h. So, this z plus h is equals to Th over W multiplied by 1 over cos phi minus 1. So, up till now this is fine. Now, you find out the expression. So, we have to simplify this tan phi term. If you were, our main goal is to obtain two things. One is the tension T and the other is the length of the chain cable. Okay. So, there are two things which you have to find out. Now, what is the formula for x W divided by Th? X W. So, you use the second equation. So, this becomes x 0 is 0. So, this becomes simply x. So, from this equation you get x W by Th is simply log of. So, log of 1 by cos phi is that sec phi. So, this is plus tan phi. Now, from this you obtained two expressions. So, actually if you simplify this will be e raised to the power x W divided by Th. So, this is equals to how much? So, this will be 1 plus sin phi over cos phi. Now, similarly you find out e raised to the power minus x W Th. So, this will be how much? This is just the reciprocal. So, this will be so there is simple maths. Now, those of you who are coming late, you just write this down. So, I am just using expressions from your previous expressions. Now, there is one important thing after this, you find out the expression for sine hyperbolic x W over Th. I have given you the expressions for the exponential e term. So, from this you find out sine hyperbolic and cos hyperbolic. These are two hyperbolic functions. And then you simplify. You simply write down the expression for sine hyperbolic x W by Th. So, those of you who do not know, you simplify this. So, this is your half, you substitute the values of e raised to the power. So, what is the equation? Plus or minus? Minus e raised to power minus x W by Th. So, this is your expression for the sine hyperbolic term. So, now you substitute the values. So, this will be how much? So, this is half of 1 plus sin phi over cos phi. This will be minus cos phi over 1 plus sin phi. So you simplify this and you get a very simple term. So you just carry out the multiplication. So this will be 1 plus sin phi whole square. So this in your denominator you will get, this is cos phi multiplied by 1 plus sin phi. And on top you will get with 1 plus sin phi whole square, this will be how much? 1 plus 2 sin phi plus sin square phi, and this one will be cos square phi. So this we are getting half. Now numerator, what is the value of this? So denominator is still cos phi into 1 plus sin phi. So you will find that 1 plus sin phi you can bring it out. 1 is sin square phi plus cos square phi will go. So sin square phi will be twice sin square phi, isn't it? So you bring this out, 2 sin phi out. So this will be 1 plus sin phi. So you are getting a very neat term. So here, so half your this will cancel, this will be simply, so very neat equation. So your sine hyperbolic, now similarly you find out the expression for cos hyperbolic, that will also come out to a very simple term. Now we will use these two expressions in our calculation. So what is the expression for cos hyperbolic? So this is cos hyperbolic xw over th. Now you similar expression you use, I have given you the expression for the e values, exponential values. So this will, instead of minus you write this as plus. So there are plenty of assumptions we have to make here. So the one that is of importance is the condition on the seabed. So you just simplify this, you tell me how much you get. You substitute the values that we have found out. Sec phi, yeah, you are right. Now this TH that we have drawn, TH is balancing your T0 component, isn't it? Anyway, we will use that later on. So this, if you break this down, this will be half of this is 1 plus sin phi over cos phi. This will be how much? 2 sin phi plus sin square phi, because you are getting 1 cos square phi, that is creating the problem. So this will be half of 2 will come out. So this is the answer. Now from this equation, so what is the expression for S? Chain length. You look at your previous equations. TH by W tan phi. So S we have started out with, after simplification, this becomes, this is at seabed condition. So this is TH. Now what is the expression for tan phi? So S equals to, this is the hyperbolic term that we will be getting out here. So this is coming as sine hyperbolic x w by th. So we are getting rid of the, angle, that is this phi. But here you have to know, so W is already known, so that you can weigh the chain cable per meter, that will give you the W of the weight of chain cable per meter, that is it in the immersed condition. So here, but this x is the variable. Now TH, do we know TH or not? There is a horizontal tension. So TH is how much? T cos, that we have found out from this expression, T cos phi. No, if you know the angle, you can find out that TH expression, TW cos phi. So only unknown is, variable is x. If you know x, you can find out length of chain cable. Now this is one expression we can use, and the other expression is, what is the expression for Z plus H? So remember we started out with, what was the expression? So x minus x 0, and the other expression that we have got was the Z plus H. So that is again TH over W. So 1 by cos phi you replace. So we are getting this as TH over W, (1 by cos phi minus 1). Now you replace this 1 by 1 over cos phi. So 1 over cos phi is cos hyperbolic. So you are just getting rid of the phi angle. So 1 by cos phi is cos hyperbolic. So but outside you write TH over W. So this reduces to the hyperbolic term. So cos hyperbolic of x W over TH minus 1. So here what are the unknown parameters? So again TH W you know, So, x is the unknown term, h you already know. So, from this you can find out z. So, now the other things that are remaining is line tension T, which is our primary focus. You calculate line tension T. So, I will just give you the expression. Your line tension T you can find out from the corrected tension, that is T prime is equals to how much? T minus rho g z a. Now, you find out from this expression. And the other expression that you require. So, this is 15, 16 and this let us say this you put this as 17. The other expression you will be your z plus h equation. Now, from this z plus h equation you get z plus h. This z plus h multiplied by w is what? Th. You can write 1 by cos phi if you want to keep the angle out here. So, or if you want to dismiss the angle, you put the hyperbolic term. So, this is 1 by cos phi minus 1. And the expression for T prime naught, we have derived the expression for T prime naught. It is somewhere, I think last class we have done that. Now, you tell me this in terms of T prime. There are too many equations actually. So, in terms of T prime, what will be the equation that we have calculated? This is at water surface, we are getting this as TH, but yeah, you have got this expression. So, this is your T prime naught is T prime multiplied by cos phi. Now, what about TH? So, we have said T prime naught equals to TH, isn't it? So, therefore, TH is also same expression. TH is also T prime cos phi. Now, this expression for T prime is equals to T minus rho g z a, and this is equals to this TH over cos phi. So, now we are getting this thing, but still our problem is we are getting the phi term. So, you get rid of this phi term. So, how do you get rid of it? So, 1 by cos phi is how much? See, we have derived this 1 by cos phi. That expression for that hyperbolic term will come, cos hyperbolic, but then again this expression will come out T minus rho g z a, but you don't write in the hyperbolic terms. If you write the hyperbolic terms, this will be a little bit awkward. So 1 by cos phi is z plus h cos hyperbolic. I want to get rid of this. We can use this expression. So this expression is say 15, 16, 17. So from this we can use. There is no hyperbolic term out here. So then what happens? So T minus this is equal to T prime TH by cos phi. So what is this expression for TH by cos phi? So this you find out from this. So Z plus H is equals to TH over W. 1 by cos phi minus 1. Take it inside the bracket, so this will be W multiplied by Z plus H. So this is equals to how much we are getting out here. So this will be TH over cos phi minus TH. This minus TH is coming. So our expression becomes how much? Our expression becomes TH plus W multiplied by Z plus H. So we have got rid of the hyperbolic term, otherwise it will create problems. So now from this equation you can get T. So what is the equation for T? So ultimately, so we are getting, this is say equation number 18. So from 18 we are getting the expression of T is coming as TH plus W multiplied by Z plus H plus rho g Z A. So we have got this expression. Now can you simplify this further? So this you try to bring this out. So here Z is common, so we can bring this out. So this is TH plus W into H. Now Z is a common factor. So this is plus W rho G A multiplied by Z. So this you can calculate, provided you know the parameters which should be known are W. W is the weight of chain in water. Rho G, of course, the density and all that you know, cross section of the cable you know, but you should know Z, the depth at which you are doing the calculation. From there you get the T. So T will come out somewhere here at a particular Z. So this point. So this is the Z point you have to find out. Can't see. Oh, sir, this one we have not. No, what I am talking about is at a particular, so this is the expression that we are getting. So if you want to calculate the tension T at a particular Z value, that is at a particular depth from the surface, now you can calculate that. So because all these A is the cross section area of the chain cable, rho G you know, W you know. Now this H is what? H is the depth of water. The only thing that you have to find out is TH. So TH is the W cos W phi water flow. So this you can use. So now the other expression that we can find out after we have found out this, the next point is, so from this diagram, this will make it amply clear. So, this distance is minus h, isn't it, or rather you can write h, whatever it is. So, now your catenary is in this form. Now, the t that we have found out as a particular z value. So, you take a tangent at this point and this is your t. Say this is your angle phi. Forward. And this is your th. Now, what is this? So, this is your water plane. So, this is your TW and this is your phi W. So, what I am talking about is that you have to know this value, depth. So, at this you can calculate the value of tension T. Now, you find out the other point is TZ, and then the parameter is the minimum length of the chain cable. Your TZ, your Z direction is in the upward direction, you find out the vertical component. So, how do you start? So, T prime Z, that is the correction after the water pressure, is T prime cos phi or sin phi? T prime sin phi. So, this is your equation. So, now you differentiate both sides. So, d of T prime Z is how much? You find the differential of this expression, that is T prime sin phi. Now, mind you, both are changing. So, that is T prime is not a constant. So, this will be how much? So, this will be d T prime differentiation by parts. So, the other term you keep it as constant sin phi plus, what is the differentiation of sin phi? So, this is cos phi, and d phi will come and T prime will come. Now, you substitute these two expressions. Now, at the beginning we started out with this d. What was the value of dt prime? That is W sin phi ds, and the expression for T prime d phi was W cos phi ds. Now, you have to use these two expressions and substitute. So, this is your equation. So, the one that we have derived, so that will be equation number how much? So, let us say this is our equation 18 and this is our equation say 19. So, we substitute in 19 and see what happens. So, dt prime is this one and T prime d prime you just simply substitute this. So, substitute these two expressions in 19. but you will be getting only dTz. So, this becomes the first term becomes W sin square phi ds. Second term. So, your T prime d phi is again W. So, this will be again W cos square phi. So, this is W cos square phi d phi, isn't it? So, sorry, this will be ds. So, now you can take out the common factor. So, dt prime z. So, you can take out W ds. So, you get some beautiful equation. So, this is sin square phi plus cos square phi, which is equal to 1. So, we are getting simply this as W multiplied by ds. So, d of T prime z. Now, you find out T prime z from this equation. So, how? Now, if you want to find this out, you write this dt prime as d of, can you write like this? Now, although W is a constant, you can take it inside. So, that means we are getting T prime z is equals to W multiplied by S. So, in physically what is the meaning? Physical meaning is the horizontal component of the tension is balancing your weight. Sorry, not the horizontal, the vertical component of the cable tension, and the horizontal component is balancing TH. So, W is a constant. That you would leave out actually. Again, you just simply integrate both sides. So, here it will come. So, this is your differential actually. So, this expression you remember. So, if you integrate the differential, you will get the original equation. So, this is equation number how much? So, this is, let us say this is equation number 20. So, two important relationships we have derived. One is your tension T and the other is Tz. Now, the other component that is remaining to be found out is the find minimum length of chain cable. So, you just tell me when the minimum length will occur. Or when do you get the minimum length? When there is maximum tension in the chain. You can just take your keychain and see, you just pull the chain, and then if you increase the tension, obviously the length of the catenary will shorten, isn't it? So, here also similarly you will get this equation. Now, let us try to derive this. Find minimum length. So, you have to calculate this L minimum. Now, remember we have already found out the expression for S. So, you use that expression. So, this is minimum length L minimum of chain cable. Now, the catenary, say this is your mean sea level or the water line. Now, your ship or barge, whatever you have taken, is floating at the mean sea level. So, like this. So, let us say that this is your mean sea level. Now, the chain is hooked up at the anchor winch. So, it is assuming some kind of a form like this. Now at this point it will start lying horizontal on the seabed. So that means to some extent it will come horizontal, and then you have an anchor. So this is your angle, that is, if you take the tangent out here, so your angle is becoming phi w. So LS is this length. You start from here, don't start from the anchor. So this is your anchor point. Now LS is this one, that is the length of the catenary. This you take from this boat. Now what is your L? If this be the length of LS, then what is your L? So this distance is your L. Now you take the horizontal and vertical distances, so your depth of water is h. You give the proper sign also. So here, so this one is x. So actually in the derivation of our formulas, that is our expression for tension, there are too many substitutions we have used, isn't it? So it's better you work this out in your hall, otherwise during exams you have trouble. So this of course is taking this also as x. Anyway, this diagram we will have to use. Now there is one assumption, is you assume gravity anchor. Now what is the speciality of this gravity anchor? Now there are a number of types of anchors you will find. Your the marine engineering terms, if I have one is gravity anchor, the other anchor is called, anchors can be of different types. Anchors, you have first is gravity, but normally these gravity anchors are used only for anchoring, say, offshore huge large structures, say offshore platform, TLCs and all these things. Number two, you have the what is called the stock anchor. So sometime in this class you just remind, if I get the diagrams of this type of anchors, and I will show you. Then you have stream anchors. These are the smaller varieties of anchor. This is only to be employed in rivers. So these are called stream anchors. The last one you will find 1, 2, 3. They are called piled anchors. Now, anchor is actually a pretty common term in civil engineering, although you have in naval architecture we mean that anchor means you are dropping a weight onto the seabed, which is actually clawing the seabed or going inside the seabed and giving a horizontal force. But anyway, so these are various types of anchors you can use. Now anchors, when you use these anchors, they are to be used with a certain what is called chain cable. I don't know whether you have this subject on this thing, mooring systems in your ship design. You will find chain cables are really not your this key chains will look like this. I will give you the diagrams. So here you have this sort of ring is going to come. So these are called studs. Now mooring systems, if you want to analyze, there is not just one simple catenary chain. Normally ships, offshore platforms, they are not moved by one chain cable. You have say another chain cable out here, or you may have as many as in one corner of the say boat, on one corner of the semi-submersible, you may have as many as 3 chain cables, one in this direction, the other in this direction and this direction. You can never moor a ship with one chain cable. That means the offshore platforms are literally held in position by these sort of, this is called a spread mooring system. Now you can just understand the mechanics, the trouble we had with only one chain cable. Now if I give you a configuration like this, you have to calculate the total forces that are coming onto this structure, the mooring forces or the restoring forces, coming from as many as how many? As many as 12 chain cables. And not only that, nowadays actually the Jaw of the Naval Act, you will find they ask you that you find out whether the ship will be able to be in position with say one chain cable snapped. Say I cut one of the chain cables, or I cut these 2 chain cables. Now will my ship still be holding in this position, or it will start drifting away? So that is another part of mooring analysis which is done. So in mooring analysis, the picture is not this simple, just the equations that I have worked out, but first of all there are 3 types of analysis that I told you. This is the first one that you do is the static analysis, then quasi-static and then dynamic. But here there are actually so many chain cables, and here you have to find out the what is called the coupling of all these forces. Coupling terms will come. So this will try to, I will try to analyze this in your later classes. So the whole mooring system, if you want to analyze, you have to analyze all the chain cables and all the forces coming from all these chain cables to the ship, and whether you are able to restrict the response of the ship sufficiently. So this, all these chain cables will exert what is called a springing force. You will come to this, we will have to calculate stiffness. So this is called line stiffness. Line stiffness you have to calculate. From this you calculate the spring force or the restoring force. So you can see the mooring analysis is quite complicated. Just in our class, the example they just dealt with only one line, but ultimately you will find you have to make a dynamic analysis with all these chain cables. So normally if you start doing this expression, you land up in a sort of a finite element idealization or a matrix form of equations. So ultimately you come into a FEM analysis. Now this FEM analysis is also not very simple, because in the in this we have assumed that there are no hydrodynamic forces acting on the cable line. That means we have vanished the F and D terms. You remember at the beginning when we started simplifying. So that is also a very dangerous assumption, but since for this is simplified the case, then we are saying that that is equal to 0, but all the hydrodynamic terms will also come, and then you do what is normally done a FEM analysis. So, this is called a FEM beam analysis. I will try to give you some exposure if you have some time. So, analysis YSIS, I think. So, this is your term. So, FEM beam analysis has to be done for all these chain cables, and not only that, there will be coupling of all these terms. So, nowadays the present method is you do straight away you start doing FEM. So, FEM is you do the static as well as dynamic analysis. Now, with lot of your restoring forces. So, in our equations, we have to start off. If you look at your dynamic analysis, so the equation is, now all this you will get in matrix form. So, this is your Kx. Now, the right hand side is what? Now, this actually we have in our calculation, we have not calculated this. Have you thought about it? We are simply assuming a winch tension out here, isn't it? So, with that we have calculated, but how, from where this winch tension is coming? So, this mooring analysis is usually done from FT calculation, that is your environmental loads. So, this is a, so you have to find out this first, environmental load calculation. So, unless you do this, all these equations that you have done is useless. So, we are assuming a certain winch tension, of course, that is, this is related to what? TW and TH. This is maximum, obviously this is maximum winch capacity, isn't it, that we have assumed. But a winch capacity calculation we have done from what? This equation. So, this is your starting point. Now, environmental loads you will find. So, there are the number of environmental loads. So, here I do not know in your hydrodynamics class you will come across. So, first one is what is above the ship is your wind force. Now, ships are normally floating in water. At the water line you will have wave force, and I do not know whether you have come across this. This is another force which is called a drift force. So, these are your environmental forces, and down below you have current. So, these are your environmental force calculations. So, this FT term you have to find out from these forces. So, that is your starting point, and this C I will talk about later on. Your C is your, this is called a cable stiffness coefficient. Now, how you find out K? We will come to this. K is called this is called spring stiffness. So the whole mooring system has some kind of a springing action. So this is called a spring stiffness. So all these stiffnesses you have to calculate it. So anyway, so you start from here, then you find out this K, C and M, of course you know from the disposition of the cable, but your final aim is FEM static and dynamic analysis. So anyway, so that will be quite complicated, but we have to stop our discussion with this. Now the minimum length of L minimum of chain, the last item that we have before we complete, this has to be calculated. Now the assumption that we are making is gravity anchors. Now gravity anchors, the main point to be remembered about gravity anchors is that they can only exert horizontal forces. So this we will use this in our calculation. So those of you who are interested, they can look any ocean engineering journal for mooring and anchoring systems. Mooring and anchoring systems are very important for offshore structures. The other important point that you want to find out is piping. Piping, I don't know whether you know anything about piping or not, but piping is actually the realm of your mechanical engineers, but some portion you should know. Unless you know that, you will not be able to design your risers or your conductor pipes. Piping layout is quite complicated. So we will break for some few minutes and then we will do this calculation.